Hello and welcome to this chapter on linear regression. Hopefully it'll be a review for most of you and you've seen linear regression before, but we're going to dive in a little deeper. So the question is how do we get to the point of coming up with linear regression? And what linear regression helps managers do is look at the relationship between two or more variables and see if there is something that they can be used for to predict. So here we have an example that a manager is looking at the relationship between advertising dollars and sales. So a marketing manager might want to predict sales for a given level of advertising expenditure. So that's only a y variable, that's what you want to predict, and the dependent, that would be the dependent variable, and the other variable would be considered an independent variable. And when we talk about linear regression, there's simple linear regression and there's multiple linear regression. So with simple linear regression, that's regression analysis for which any one unit change in the independent variable, and we usually call that x, is assumed to result in the same change in the dependent variable y. So a change in x results in a change in y. So that's the independent variable and y is the dependent variable. We could also have multiple linear regression where we have several independent variables that are used to predict y. So the first thing we're going to talk about is just a simple linear regression model. And when this model gets calculated, it's usually written in the following form. So y is equal to beta naught plus beta 1 x times x plus e. So the characteristics of the population are your betas. Beta 0 or beta naught or beta 1. Then you have a random error or error term, I should say, that's at the end that makes up the differences for what's not being explained by this part of the equation. Sometimes you also hear the equation for a line equal to y is equal to mx plus b, where m here would be the beta 1, which is the slope of the line, and then b is where the line crosses the y-axis. And we'll say more about that later. I hope you follow along in the book. I'm opened up a file named the Butler Trucking Company, and it's the name of the file is just Butler. So it's got 10 observations and it's looking at the number of miles traveled and how much time it took for them to actually make their deliveries. So what they want to try and do is predict the number of miles. Does that predict how much time you spend? And so that's what they use for the first example. And we'll continue on with that. So as we're trying to come up with this regression equation, some things you need to understand is that we don't know what beta 0 and beta 1 are. So those are part of population parameters. Just like we've done with everything else, though, we can use some sample statistics that can be estimated to determine what beta 0 and beta 1 are. So when you see the big B's here, that's part of the population. And the lowercase ones are part of the sample statistics. So we're trying to come up with a regression equation. So now notice it's y hat, the little, I think, greater than sign on the top is equal to b0 plus bx. So that's the mx plus b line equation that I was talking about earlier. So notice that this is an estimated linear regression equation, and we hope that this estimate will be representative of the actual line. So that's slightly different than this line here. So that's a linear regression model. So using this model, if we wanted to predict, say, how much time would be spent if we knew the driver had to drive 75 miles, all we'd have to do is put 75 into this model, multiply it by B1, and add the B0. So some more terminology and how you talk about things. So with this simple linear regression model, y hat is equal to B0 plus B1 times x. We see what y hat is the estimate for the mean value of y that corresponds to a certain x. B0 is the estimated y-intercept, so that's where the line crosses the y-axis. And B1 is the estimated slope, which means a change in x results in how much of a change in y. Or I should say one change in x results in a certain amount of change in y. So notice that this is just an estimate for the simple linear regression. And then y hat becomes the point estimator for the expected value of y given x. So another way of thinking about everything we've talked about is you typically have your regression model. So now these are using the betas. We have our sample data in its most simplest form, 1x, 1y. Then we get an estimated regression. Now we're doing y hat and B0 and B1. And we assume that B0 and B1 are the estimates for beta 0 and beta 1 in our regression model. Later on, we can do some tests to see how confident we are that these are good estimates for our betas in the regression model. If we were to visually look at lines, we can see where that y-intercept is, or B0, in our different types of relationships we might have. So this line, as we increase in x, the value of y is going up. Let me see if I can draw that out for you. Change colors a bit here. So as we increase in x, you see there's a slight increase in y. Same thing here. So that would be our y value for our x value that we have. So that is a positive slope, so a positive linear relationship. If we have x here, let's say we choose 1x here, we can see that that value went down from B0, and so that is a negative linear relationship. If B0 stays the same no matter what x we try, then there is no relationship. So moving on, the next thing we want to do is talk about the least squares method for estimating that line or having the best line. And so the least squares method, it's a way to use your data to find the estimated regression equation. That is, we want to determine the values for B0 and B1. And as I mentioned earlier, the slope B1 is estimated change in the mean of the dependent variable y that's associated with 1 unit increase in the independent variable x. So as x changes by 1 unit, how much does y change? Because x will be 1 here, right? If we go from 18 to 19, let's say we were looking at numbers for x. X could be 18, the next value is 19. So what is that difference in change of 1 unit on y? So that's going to be our beta 1. The intercept, where the line crosses the y-axis, is b0. And it's the estimated value of the dependent variable y when x is equal to 0. So here's the Butler data again. Again, we want to find out or use a regression analysis to determine if we know the miles traveled, can we predict the time spent traveling. So here we have a scatter chart, and we show that the x value miles traveled is on the x-axis and the travel time in hours is on the y-axis. So we spread that out, and it appears that the longer travel times appear to coincide with more miles traveled. And if we could draw a straight line through these data, we would see that this is a positive linear relationship. So what least squares is trying to do, and I'm sure you've heard this before, is it's trying to draw a line, and I probably haven't drawn the correct line, such that the distance, let me change colors here, the distance from the line of all the points when squared, because some of them are negative, so you want a positive value there. When that distance is squared, we want to minimize it, and that will give us the best line. Right? So that's why it's called least squared. Now if I go back here to my Excel spreadsheet, you'll see that I've got a chart already, and Excel does a good job of going ahead and draw that chart for you. In fact, I'm going to delete the chart and show you how that's done. So you load up your data, then you go to your data tab, you're going to click on data analysis, and you're going to select the regression tool. Once you do that, a dialog box is going to come up. It's going to ask you what's your Y input range. So our Y input range, that's what we want to predict, and X is our independent variable. We could set our confidence level here, and I think your book later on sets it to 99, so I'm going to go ahead and do that now. And we'll have the output go onto a new worksheet, and for now we'll just leave that alone. So we could do some residuals if we wanted to, and we'll explain what those are later on. Basically, you just check the numbers, check what you want to see in your output, and click OK. Okay, so it gives us some information there, and we'll explain that later, but I just wanted to show you how you get that equation. We get our coefficients. So if you think of our coefficients here, let me get this line here. That would be our beta 0, we're the intercept, and that's our beta 1 or B1, which are estimates for the actual linear equation. Now to get just a basic scatter chart, all you have to do is highlight your data, X and Y columns, go to Insert, Recommended Charts. Notice that the recommended chart here is that scatter chart, so I'll click OK. Now, some nice features about this, if we move it off to the side, or even as it's on the screen here, is we can actually have Excel put in the trend line. So we click on this plus sign here, come down here and select trend line. Notice it puts the trend line in here, so it's doing least squares. It's trying to minimize the distance between each of your data points from that line. Also note that when we click on this little expand button here, we can get to more options. And the more options here, we've got linear, but we can actually say display the equation on the chart, and we can also display the R² value, which we'll talk about later. And I'll close that. So notice what happened here. We've got our actual equation on the chart, and it's written as mx plus b. It's no different than our b0 plus b1 times x. It's just reversed around. And we can see our R² value here as well. If that gets in the way, we can move that up. Just grab it. And so it's automatically done for you. Now I would move this off to the side so it's not hiding the data, but I wanted to show you how easy that was to do. So the least squares equation then looks like this. We want to minimize the value of y minus y predicted squared, which is what I was telling you is the distance from the line, or another way to write that is to minimize the y, your actual y minus b0 minus b1 x1. That's y hat if you're plugging in the numbers for that. And you want to square that and do that for every observation. You want to minimize that. So that's what's going on. So if we were looking for a particular observation, we could find its residual. That particular observation was represented as the ith observation. So the residual E sub I is equal to y sub I minus y hat sub I. Y sub I is your actual value that you had, and y sub I hat, that little caret top on top, is what your equation predicts. So this error term, again, if you think about it, is what is not being explained by your model. And that model is that equation that you wrote out. Sometimes that equation is also called the function that you're writing out. So we can actually rewrite that if we know y sub I minus y sub I hat squared is equal to, inside the parentheses here, that's E. So all they did was replace what's inside the parentheses with E. So we're just doing E squared. So that's the regression that minimizes the sum of squared errors. So from our equation then, we can see that our slope is B1, 0.0678, and our intercept B0 is 1.2739. Okay, so when you do this in Excel, let me get this so you can see it on your screen here. Notice the intercept is going to be by itself. It's not going to be multiplied by an x here. And so then this is B1. We also see that when I did that regression analysis, the intercept here, that goes with your independent variable. Not the intercept. This one, it actually says X variable out to the side. So the intercept is where it crosses the line. So if we look at that again, then you see that intercept is right here. That's how it's written. And then what goes with B1 is right here. Same value again. So I wanted to make sure you saw that and how that's interpreted. And if we had, and we'll see multiple regression, if you had others, you'll know that that goes with the next variable that you had in your equation. But the intercept always stands by itself. And so then y hat, when we write out our equation, is this intercept plus b1 times your x. So if this is the first observation, this then would be the predicted y for the first observation. And if we saw from here, we know that we've got our predicted y from the actual y is that when we subtract that, that's our residual. Sometimes that's positive, sometimes that's negative. If we square it, then we get a positive number. And what we're trying to do is minimize that distance so the line fits the best inside of all those scatter plots. So then the interpretation is such that for beta 1, if the length of the driving assignment was 1 unit, so we drove 1 mile longer because that's what x represents in this particular equation, the mean travel time for that driving assignment would be 0.0678 units. And since our units are in hours, we can then multiply that out. That's about 4 minutes longer. The interpretation of the intercept, B0, if the driving distance for a driving assignment was 0 units, because that would be where x is 0, the mean travel time would be 1.2739 units, or approximately 76 minutes. Some more terminology that you should be aware of is something called experimental region. And that's the range of values of your independent variable, in our case the miles, in the data used to estimate the model. So the regression model is only valid over this region. There's also a term called extrapolation, and that's the prediction of the value of the dependent variable, which is y, outside of the experimental region. And that's very risky because you don't have any data to support that. So when we look at that, is we know that the value here, right, starting from this low value of miles driven to this high value here, that's the experimental region. What's risky is to extrapolate in this area or in this area, because your data, you didn't carry data or didn't capture data to support that analysis. So it may be here, yeah, that looks sort of linear, but maybe in this region the data would support something that's nonlinear. And so you cannot make those extrapolation points, or at least you shouldn't. And a lot of times what they'll say, if you're taking a stats class, is that the further out you get from the end of what you've collected and what you've measured here, the higher the risk is, because it becomes more and more unknown. So let's continue on with our calculation of our residuals. So let's say we want to, the first driving assignment was the value for miles was 100. So we know, we plug that into our equation, and then y hat, the predicted is 8.0539. The residual then would be the actual observed y minus predicted y is 1.2461. So that's about 74 miles different. So we can continue doing that. We get what is the predicted. We get our residual, we square our residual, and we see what the totals are here. So with the square, notice here we've got 0. We want to minimize that distance. So when we sum them all up, that's what should happen. Also notice that the sum of the predicted y is equal to the sum of the values of the dependent variable. So notice they should be the same. So here we have the linear regression line that is predicted for y hat. So that mx plus b right here. And so that, again, like I said earlier, what we're doing is just trying to minimize this distance between our data such that we can draw a straight line if it's a linear relationship. So notice how the line here underpredicts what the value should be, and then the line in these areas for these two data points overpredicts what y should be. Again, visually, if we see this distance and we can square it, then we have a square here, and so what this line is doing is minimizing the distance above and below the lines for these data points. And I've already demoed how that you can construct that scatter chart with Excel charting tools. You right click on I do the elements, but you could do a data point and add the trend line. From the trend line, you can expand that out and scroll down and add the equation and the r squared value. And that'll give us something like this. So if I just wanted the equation, it would just be this. I highly suggest that you open up the file, the data file, and try and do this on your own to make sure that you understand how it works and how simple it is. So for those of you that want to work things out by hand, you can actually calculate what B1 and B0 is going to be. So if you do your x minus your mean of x, get that subtracted, times the difference between your actual y minus the mean of y, and then sum all that divided by the sum of your mean of x subtracted from your actual x squared. That gives you beta 1. Remember, it's a change in x. If a change in x by 1, what is the output or the change in y? So b sub 0 is just your predicted y or average y. I should say average y, the mean value of the dependent variable, minus your b1 times your mean of x. And so to me, it's a lot easier just to let Excel or some other statistical package calculate that out for you. And I'm going to pause here. When we come back, we will talk about assessing the fit of the simple linear regression model.